Hey yo, what's up, YouTube? It's your boy J O. What the JBRAHAM. This exercise is essentially the local alignment version. Design a function in the general way that is the sequences, gap penalties, and scoring matrices should be supplied as arguments. The function should not print any output and should only return the final score as well as its corresponding alignments. Note that the highest score can lead to the multiple alignments. The main program function should then print the score and alignments to the standard output. The command line interface should be specified as follows. Smith-Waterman does local alignments, meaning you find it the best matching subsequences between two sequences rather than aligning the full length. It uses affine gap penalties, which means there's two separate penalties, one for opening a gap and extending a gap. Yeah, this is more biologically realistic than singular linear penalty. Okay, I do remember the Smith-Waterman algorithm. Like I do remember doing this. Input two sequences, scoring matrix, gap penalties, one for opening and one for extending. Matrix setup. You'll need a dynamic programming matrix for scores. Because of the affine gaps, you usually maintain three matrices. You'll need a dynamic programming matrix for scores. What? Because of the affine gaps, you usually maintain the three matrices. Mm-hmm. Yeah, yeah, yeah. Ah. So you have to maintain three matrices. Okay, I get that. Oh. Mm, I still have my doubts on how the Blossom and Pam affect this matrix that we are making for for M X Y. Okay, let me clarify this in a way that directly connects Blossom with the find gaps. Role of scoring matrices. The scoring matrix tells the algorithm how good a match or mismatch is between two amino acids. The scoring matrix tells the algorithm how good a match or mismatch is between two amino acids. For example, score matrix AA, the usually positive, which score matrix. Every time you consider a diagonal move for your DP matrix, you look up the score for. So Blossom PAM directly affects the value you put in MIJ. I don't get it. We give in specific gap penalties, like we give in separate values. Then why? How is this? I'm still having some confusion. Scoring matrix tells the algorithm how it interacts with the affine gap matrices. It's the best score ending with gap in sequence 1. Yeah, yeah. When computing, you do not use the scoring matrix. You only subtract gap. Oh, yeah, yeah. When you compute a diagonal mismatch, you add score from the matrix. Yeah. No. After diagonal moves in M. Think of it like how good your amino acid together, how costly is it to insert a gap. Together they decide. No, can't. No, I still didn't get it. I still didn't get how the PAM and Blossom works here. Maybe it's also because I still don't know difference between them. So I want you to give me an example that would answer give me an example that explains these. Pam and Blossom, because when I did the needle matrix on paper, I don't think I used PAM or matrix in any form. All I remember are the gap penalty and the gap extension. I see exactly where the confusion is. Empirical measures of how often amino acids actually substitute in conserved protein regions. Key point: both give a score for matching any pair of amino acid, but the way the scores were calculated differs. PAM is evolutionary based, Blossom is observational/conservational based. Then what's blast PSI? PSI blast and normal blast. Alan Avon. Without a matrix, you just do can only assign, yeah, gap penalty. Each diagonal score is looked up on the matrix. A versus A. So when filling the DP table, how PAM differs from Blossom here. If you use PAM 30, the scores might differ. What? I need to understand more, I guess. Good for closely or distant related sequences. Tells you after X mutation how likely is the substitution. Wait, wait. If PAM does what it does, then what's with the PSI blast? They seem similar. Uh, PSI blast is an iterative search algorithm, not scoring matrix. Okay, okay. Position specific iteration blast. Okay. Oh, Pam and Blossom. Rules of the game. A smart player who updates the rules as they see more players. Okay. I'm kinda starting to understand, but could you still again tell me with an example how Blossom and Pam have different use cases? Oh. listen hard. Sitting on a counting dollars, you been counting stars. Baby, I've been losing sleep. Imagine two protein sequence. Okay, these are amino acid sequences, not genetic DNA sequence. Amino acid. Mhm. Using substitution matrix, PAM matrix derived from evolutionary models. Do you know what? I think I should use YouTube because I'm still having confusions on PAM and PAM matrices. Who got a better explanation? Pam and Blossom scoring matrices. Class 4 Plam versus. Let me first see Rob Edwards or Bio Pundit. In this video, we discuss the importance and conceptual aspects. Okay. What are the conceptual?
Hello, and welcome to the technical section of BioPandit. This is Saurabh, your very own Mahapandit, and today I am going to discuss about PAM substitution matrices. Suppose you have two DNA sequences. You
Mm-hmm.
can align them in two different ways. Which one is the best alignment? Well, The best alignment is the one that best represents the matches among different characters. So let us just define a matching algorithm. If there is a perfect match, such as A matching with A, T
Mm-hmm.
with T, G with G, the score is 1, otherwise 0. So, following this simple algorithm, these are the scores of the two alignments. The alignment with the highest score is the best alignment. The score matrix becomes more complicated for protein sequence alignment. Why? There are two reasons. First, the alphabet size has increased from 4 to 20. In
Mm-hmm.
DNA, there are only 4 bases, but in protein, there are 20 amino acids. The second reason is for proteins, the scoring scheme of 1 for a match and 0 for a mismatch is not enough. Think of a protein complex. Hydrophobic interactions between a methionine and an isoleucine amino acid contributes most of the binding energy. In this case, a methionine to leucine substitution can have a very different impact on fitness compared to a methionine to arginine substitution. Methionine to leucine substitution conserves the hydrophobic interaction because both amino acids are highly hydrophobic in nature. But a methionine to arginine substitution will disrupt this interaction as arginine is charged. This means to maintain this interaction in the course of evolution, methionine to leucine substitution is more likely to occur than methionine to arginine substitution. In other words, amino acid substitutions are too complex to be modeled using a scoring scheme of 1 for a match and 0 for a mismatch. So, in terms of how likely a certain substitution is, some substitutions should be given a higher score as compared to the others.
Mm-hmm.
The factors that influence the probability of mutual substitution are so numerous that theoretically predicting a substitution matrix is almost impossible. Rather, we derive such matrices by directly computing the actual substitution rates from real protein sequence alignments. Percent accepted mutations or point accepted mutations or PAM is one such example. These are the basic assumptions of PAM matrices. The PAM matrices are based on a mutational model of evolution which assumes that amino acid changes occur as a Markov process, with each amino acid change at a site being independent of the previous changes at that site. PAM matrices are based on predictions of the first change that occur as proteins diverge from a common ancestor during evolution of a protein family. Matrices that may be used to compare more distantly related proteins are then derived by extrapolation from these short-term changes, assuming that these more distant changes are a reflection of the short-term changes occurring over and over again. For longer evolutionary intervals, each amino acid can change to any other with the same frequency as observed in the short term. Each PAM matrix is designed to compare two sequences which are a specific number of PAM units apart. Two sequences S1 and S2 are at evolutionary distance of 1 PAM if S1 has converted to S2 with an average of 1 amino acid substitution per 100 amino acids. For any specific pair of amino acids, like here M and L, this number included in the PAM 100 matrix reflects the frequency at which M and L are expected to replace each other in two sequences that are 100 PAM units diverged. In order to calculate this, first we need an alignment. Imagine any two amino acids A and B. If they are included in the same alignment column, we consider either A to B or B to A substitution has occurred. We first calculate the probability of occurrence of amino acid A. This is just the relative frequency of occurrence of that amino acid over the entire alignment. Second step is to calculate the number of times A to B or B to A substitution has occurred. This is FAB. Third step is to calculate the number of times A gets substituted into any other amino acid. This is given by this expression. If A and B are same, this means that we are calculating the probability of A remaining unchanged during this interval. This is based on relative mutability of amino acid A, which is given by this expression. The mutability of an amino acid is a measure of how much it changes in the evolutionary period of interest. Thus, MAA, which represents the probability of remaining unchanged, is given by this. This 100 reflects the fact that the unit of evolution used in this model is the amount of evolution that will change 1 in 100 amino acids on average. This is referred to as 1 PAM evolutionary distance. Now, if A and B are different, the probability of A changing into B can be computed as the product of the conditional probability that A will change into B, given that A changes, times the probability of A changing. This is the expression. Now we can define scoring matrices. The score is calculated as this. Let me remind you guys that in this process, you have generated a 20 by 20 matrix. Positive elements in this matrix represent that substitution between two amino acids are more likely than random. Negative values represent substitutions between the two amino acids are less likely than random. In a Markov model of evolution, substitutions are independent of their past history. So if you have PAM1, you can continue extrapolating the same matrix over and over again to cover as much evolutionary divergence as you need. If you multiply PAM1 twice with itself, you get PAM2. So simple matrix multiplication gives us the higher order of PAM matrices. PAM100 is PAM1 multiplied 100 times. PAM250 is PAM1 multiplied 250 times. So this is all about PAM matrices, guys.
Hey yo, hey yo, what was that? What was that? Bio pundit. I mean, I, I don't get it, bro. That was a lot. Okay.
Spare bis zu 70% auf alle Bettdecken und Kopfkissen. Jysk, Scandinavian Sleeping and Living.
Took me forever to realize you're writing mirror. Great presentation, kudos.
One of the first people to really understand that in a very different way is a really amazing scientist called Margaret Dayhoff.
Yeah, I think I heard this name during class.
She was at George Washington University in Washington, D.C., out on the outskirts of Washington, D.C. And Margaret Dayhoff, early on in the history of kind of sequencing of different organisms, published what was called the Protein Atlas. And this is back in the 1970s, okay? So we only had 3 or 4 sequences, maybe a dozen, maybe 100. Not very many sequences. And in fact, the very first version of what Margaret Dayhoff eventually developed into being what's called the point accepted mutation rate started with about 71 different protein families. Okay? Protein families. And so what Dr. Dayhoff did was to take these protein families and to make very careful alignments of them, and then to count every time you switch from a tyrosine to a phenylalanine, and every time you switch from a tyrosine to an aspartic acid. And in fact, she didn't just focus on tyrosine and aspartic acid and phenylalanine because that would be a bit weird. She calculated the frequencies of going from every amino acid to every other amino acid in groups of really closely related proteins. So the idea is, let's let evolution tell us how hard it is for proteins to switch from tyrosine to phenylalanine or tyrosine to aspartic acid. I said, holy moly, that's going to break my protein, but maybe it doesn't, right? But the way we can find out is by just taking a look at evolution and saying, how frequently do we see a tyrosine switching to a phenylalanine where we believe it's the same protein, and how frequently do we see it switching to azelaic acid? So Dr. Dayhoff took proteins that were greater than or equal to 85% similar, and she looked at 1,572 changes among those proteins. And she said at each point, this is the frequency with which a mutation is accepted, and hence it became the point accepted mutation table. A little bit later, Stephen and Georgia Heinkoff, Margaret Dayhoff did this starting in the 1970s, but really carried on for a very long time, studying this phenomenon. The Heinkoffs did this starting in 1992, and they took a slightly different approach, which was to take protein alignments, and what we haven't really talked about yet, but we will get to, is that very often proteins have what are called domains that are very, very highly conserved, and then the rest of the protein is very different. And this is evolution just cheating. The idea is that if you figured out how to do something, let's just use what we figured out before, let's not figure it out from scratch again. So for example, one very common domain is called a dehydrogenase. And so what that means is that you've got two chemical compounds like those two that I just drew, and one has an H and one has an OH, and you take those away and you get H2O. And so all that dehydrogenase means is you're just taking away water. This is a really common thing because when you do that, whatever's bound here and whatever's bound here, you can stick them together. Okay? So once we figured out how to take water away, we don't need to go and invent that from scratch, right? We can just steal it. And so what the Heinkoff said is, hey, there are these domains. The rest of the protein may not be very similar, but there are regions that are really similar. And so if we take, you can call them domains, or you can call them blocks. If we take blocks, we can basically do a very similar calculation as Margaret Dayhoff did, and we can come up with an exchange between the frequencies with which amino acids change between different positions. So we have two slightly different versions of the same thing. On this side, it's called blossom, and on this side, it's called PAM.
Mm-hmm.
And depending on your personal preference, you can basically use either of them. And for each different version, there are also different versions. So the common versions of PAM are 100, 120, 160, 200, 250. And what this means, this is the number of mutations per 100 amino acids.
Mm-hmm.
So this means you have 2.5 mutations per amino acid, okay, expected. And it's basically how similar the proteins are that you put into the table to do this calculation to calculate the frequencies. And then in blossom, a very typical range of blossom matrices would be somewhere around this range. And the numbers here are the percent identity of the proteins used. So the proteins that make up the blossom 90 matrix were at least 90% identical. The proteins that make up the blossom 80 matrix were at least 80% identical. And these two numbers are sort of like PAM 100 approximately blossom 90, not really, but kind of, okay? So as this number increases, as this number decreases, you're getting more divergent proteins. Most everybody in the history of the world uses BLOSUM 62 simply because, anybody know why?
Oh no,
Why do you think everybody uses the BLOSUM 62 matrix?
I think
So the reason
most
that
of the
everybody
creatures
uses the
are
BLOSUM 62
60%
matrix
similar.
is really simple. It's the default matrix in BLAST. So if you don't specify any parameters, you can say, I don't want to use BLOSUM 62, I want to use PAM 250 or PAM 100 or BLOSUM 90 or BLOSUM 45. You can change it to wherever you want, but nobody ever does that, right? Why would you change a parameter in a program? That's stupid. So everybody uses BLOSUM 62.
No, that's the stupidest explanation for why people use 62.
You're
Come
not
on.
a child.
I expected better. This takes more understanding than I thought.
Hello again, I am Mahima Bhardwaj from Bioinformatica. In this video, we will learn about PAM matrices.
Ah, it's the
Let's get
bioinformatica.
started. I assume that which was first developed by Margaret Dehoff.
Wait, just a minute. Are they? No, they're not what I expect. Okay.
Hello again, I am Mahima Bhardwaj from Bioinformatica, which was first developed by Margaret Dehoff. One of the 20 standard amino acids accepted point mutations. An accepted point mutation in protein is a replacement of one amino acid by another accepted by natural selection. It must be accepted by natural selection. To be accepted, the new amino acid usually must function in a similar way to the old one. Chemical and physical similarities are found between amino acids that are observed to interchange frequently. Now, this assumption is reasonable because this likelihood should depend on the product of frequencies of occurrence of two amino acids and on their chemical and physical similarities. The mutation data were accumulated from the phylogenetic trees and from a few pairs of related sequences. If we see a simplified phylogenetic tree, here 4 observed proteins are shown at the top. This is first one, second one, third, and this is fourth protein. Infrared ancestors are shown at the nodes. These are infrared ancestors. And amino acid exchange are indicated along the branches. These are amino acid exchange. Here we clearly see that A changes to D and A changes to C. But C and D do not directly interchange. If we had compared the observed sequences directly, we would have inferred the change of C and D also. For these, we have treated the changes statistically, distributing them among all observed alternatives. This matrix is of accepted point mutations derived from the tree we have discussed right now. In the matrix of accepted point mutation, we put
It's already 9.
Replaced.
So I realized 2 things. I realized that I still don't know PAM matrices. I thought I would understand this much faster, but no. Yeah, I get it. It's PAM blossom. I think I have to read this. Yep, that's... Gosh. I have for each pair, choose at least 2 different blossom. Okay. So read for a defined Smith-Waterman affine sequence 1 gap extend, initialize matrices. What? Trace back pointers. Mm-hmm. What? Okay, I'll build it step by step. Brr, brr, skri, pop, 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 skibidi, bidi, bidi, bidi. Mm-hmm. You first take the substitution score for Matrix. What does that mean? Ich hab das nix verstanden. No. No, no, ich hab das nix verstanden. You know what? I'm gonna end the stream. I almost got it. I know how to make this program. I don't know how to write the program. Uh, yeah, I'm gonna end the stream because I don't think I'm gonna be productive now. I'm gonna end the stream. I have work tomorrow. God damn it. I mean, it's not a big deal. I can still do it. I have exams coming out. Yeah. Peace out, YouTube. And